All right, so we are in time here. So I'm going to write something in the board here, and then we explain this slide. Yeah. So let's say you have a central atom here, a big atom, and around this atom there are 3 pair of electrons. So 1 pair here, 1 pair here, and 1 pair here, like that. So you can write like this way, or you can also write like this way. So 1, 2, 3, the same thing. So this is pointing this way. So this is 1 pair electron, this is another pair electron, this is another pair electron. So if you see something like this, so central atom is surrounded by 3 pair electron, 1, 2, 3 pair electrons. So the most likely, the most stable structure of this one is, this is 120 degree bond angle, 120 degree bond angle, 120 degree bond angle. Everybody got that? So this is the most stable. So yesterday I told you, if central atom like carbon is surrounded by 4, 2, 3, 4, the most stable bond angle is 109.5 degree. Everybody got that? So if central atom is surrounded by, look here, so this is the central atom here in the center. So it is surrounded by 1 pair here, another pair here, another pair here. So this is the bond angle between this and this is 120, this and this is 120, this and this is 120. Make sense? So it's like a, in a plane, like that. And so this is how many pair? 4 pair electron. 4 pair electron here. So 1 pair, 2, 3, 4 pair. How many pair here? 1, 2, 3 pair. So let's make a 5 pair here. So let's say central atom here, and it is surrounded by 5 pair electrons. So 1 pair here, another pair 2, this is 3, and then I need to put another 2 pair somewhere. So 4, 5 pairs. So if it is surrounded by 5 pair of electrons, it is hard to draw in the board. So it looks like this. So I show you 5 pairs. So look here, this guy. Everybody got this one? So 1 pair going up to the ceiling, 1 pair going toward the ground, and this 3 pair, 1 pair, another pair in the equator here. Everybody got that? So 5 pair is very hard to draw in the board. So I'm going to draw in the board this molecule here. So how we draw this molecule is like this. So let's say this is the line phosphorus, and 1 pair is going up like this. So I draw that line up going like that. And then this going down, I draw like this. Everybody got that? And then these 3 are in the equator here. So I put 1 here. So this guy somewhere here, and then maybe I put 1 here. So like that. So like this. Everybody got that? So like this. So this 1 pair going up to the ceiling, 1 pair going toward the ground, and 3 pair here are in the equatorial region. Everybody got that? So 1 pair electron, another pair electron, another pair electron, another pair electron, another pair electron. So how many pair are there? There are 5 pair of electrons. Yeah. So what is the bond angle here? So if you look the bond angle between this guy and this guy, there is 120. This guy and this guy is 120. This guy and this guy is 120. And from this guy to this guy is 90. The bond angle between here is 90. Here is 90. And if you go down, 90. So up and down, if you look the bond angle, this is 90. And if you look the bond angle along this 2 in the equator, 120. Make sense? So like that. So it's very hard to teach in the board. It's we cannot draw this structure there. And if I have a 6, so I draw this one, right? So I just want to, so there was a 5 pair. So I was drawing this 5 pair here. So this is 3 pair, 4 pair. Now I draw 5 pair here. So 1, 2, 3, 4, 5. So these are in the equator. So this one in the equator. This is going toward the ceiling. This is going toward the ground, right? So this is the bond angle between these are 120. This is 120. This between this and this is 120. The between this and this is 120, but between this and this is 90. So this is 90. This is 90. Everybody got that? So like that. Now let's talk about there is a central atom here, and that is surrounded by 6. So 1 is going up. 2, 3, 4, 5, 6, right? So 4 are in the equator, 1 is going toward ceiling, another is going toward the ground. Make sense? There are 6 pair of electrons around the central atom. So how I draw this one is, so here is the central atom right here. So 1 pair is going up, another pair I'm holding here is going down, and 4 are along the equator. So 1 here, another here, another here, another here, like that. So along this. Yeah, it's very hard to write in the board. But it looks like this. So if you look the bond angle between this, so the bond angle between this one and this one is 90. Take the protector and measure the bond angle 90. This one is also 90. This one is also 90. This one is also 90. The between this one is also 90. All bond angle is 90. Yeah. So all bond angle are here 90, 90, 90. Although you look here, it doesn't look like 90. It looks like 20 or 30 degrees, but it's not true because it's the way we cannot draw in board. Yeah. So we need to look this structure like this. All angle here are 90. Good. So now, if you see something like this, 4 pair electron, this kind of structure is called tetrahedral. Tetrahedral. Tetra means 4. Four ways projecting. 4 electron pair are projecting to 4 ways. So it's like that. So like this. Yeah. So if we hold like this, 3 is coming toward you and 1 is coming toward me. Or if I hold like this, 1 is coming toward you and 3 is coming toward me. Right. So something like this. This is called tetrahedral geometry. And this is called only 3. So this is called trigonal. Trigonal. Because there are 3 here. So 1 like that trigonal or triangle. So 1, 2, 3, like the trigonal structure. And then this guy is called, so this guy is called like this. So this going up is called pyramid. Going down is also called pyramid. And this is called 1, 2, 3 trigonal. So in the center we have trigon. 1, 2, 3 trigon. Trigonal in the around here, and one pyramid going up, another pyramid going down. So trigonal bipyramid. There are 2 pyramids. Everybody got that? So if there are 5 electron pairs around the central atom, this is called it assumes the trigonal bipyramid structure. Yeah. So in my time there was no model. It's very hard to learn this. Now we have a model. You can just buy $10 and you can build your own model and do it. Yeah. And now this guy with 6. So here 6 pairs. So 1 pair, 2, 3, 4, 5, 6 pair here. You could say this is like a square. So you could say square, and one pyramid going down is another pyramid. You could say square by pyramid. Yeah. So center is a square, like a square thing, square by pyramid. But they decided to call is a what they call it. This one is I just forgot the name. That's a you guys look here. That is called. So this is trigonal bipyramid. This is called octahedral. So that's called octahedral. Look here, this guy. So one is going up, one is going down, and then 4 are around that equator. So this one. So this is called octahedral. So you could call this as a, okay, this is a square, and this is a pyramid. This is a pyramid. You could call this as a square bipyramid also. So square bipyramid or octahedral is same. Make sense? So they call it this as an octahedral. Octahedral. So now from based on this geometry, we can identify what is the bond angle or what is the molecular structure look like. So I just showed the electron pair geometry here. Now let's go here and look the molecules. So look here. So this molecule OF2 should look like this guy. So basically it should look like this. So O is here, and then one pair going this way, another pair going this way, 2 pair. This is 1 pair, 3 pair, 4 pair, right? So if that's a 4 pair, it should look like this, right? The molecular structure look like this, and the bond angle should be 109.5. But what happens that is there are 2 lone pair here. So here is a lone pair, here is a lone pair. So there is no this bond, there is no this atom, there is no this atom. So this space is occupying the lone pair. This is occupying the lone pair. So the molecule look like this. Look like, so there is no atom attached here. There is no atom attached here. So it looks like a V, right? Everybody got that? So OF2 looks like this. And what is the bond angle? You would predict from this tetrahedral geometry 109.5, but it's not 109.5 because this is the electron pair. This is the electron pair. They push this bond and this bond more down. So it's not 109.5. Maybe it's about 107.5. Because there is a 1 electron lone pair, 1 electron lone pair, and lone pair push the this bond pair with great force down on it. So this goes the shape from 109.5 to 107. Everybody got that? So OF2 looks like this. So this is O, this is F, and 2 electrons are pointing this way and this way. Yeah? Good. So OF2, so I will put exam question. Oh, what is the molecular geometry of OF2? It's a linear, it's like a straight line, or it's a bend. So it's a bend. Why it's a bend? Because it has a lone pair there, it has a lone pair there in other places, and so they are pushing it down a little. Everybody got that? So this looks like immediately when you see the that lone pair in the center atom like this. So this is the bend structure, and it's not 109.5 as predicted by ideal bond angle here, because this lone pair pushes the bond pair with more force. Good. So look here, electron pair geometry is tetrahedral. So 1 pair, 2 pair, 3 pair, 4 pair, pointing 4 way. But molecular geometry is like this, is a bend. Good. Like that. Now water. This again, OF2 and water look like the same. Look here. So 1 pair here, 1 pair here. There are 2 lone pair, and this is another pair. So they are based on the tetrahedral bond angle here, like it should be 109.5, but it's not 109.5 because there are two lone pair here. There are two lone pair here. So this one and this one. So they push with the great force to this hydrogen down, and the bond angle of OS to become 104.5. Yeah. So if there are 4 electron pair around the central atom, you would expect 109.5. Yeah. But if there are a lone pair, that angle becomes a little bit smaller than 109.5. So in ammonia, this angle, so there are 2 electrons out here. So you will be expecting bond angle 109 because there are four, one pair this way, one pair this way, one pair this way. You will be expecting 109.5, but since the lone pair pushes this bond pair down more, so the bond angle is a little bit smaller than 109.5. So bond angle here is 107.5. Make sense? But if you look for the water, there are 2 lone pairs. So look for the water, 1, 2 lone pairs. So bond angle is even smaller. They push more down. Good. So if there are 4 electron pair around the central atom, you would expect ideal bond angle is 109.5, and it is different than 109.5 because you have some lone pair, and lone pair push the bond pair down more, and the bond angle becomes smaller than 1. Everybody got that? So if more lone pair, even smaller the bond angle. Yeah, because it is too much like that. So this is a bend. This is also bend. This is also bend. How about this one? Are there any lone pair in this central atom? No, there are no lone pair here. So this is linear. Yeah. So this is a linear, meaning that the bond angle between this one and this one is 180. So I didn't write that one. So if central atom is there and either this way or they are this way or whatever they have, and then if there is no lone pair here, it's always 180 degree angle, and we call linear. Yeah, AX 2 times. So if this is A, X, and X, so central atom is connected to 2 other atoms. Make sense? So if a central atom has a lone pair of the electron, they immediately bend. So this is, there are no lone pair, no dots here in nitrogen. So this is linear. Now look this one. So boron, the central atom doesn't have lone pair here at the center. So boron BF3, BR3 looks like this one. Make sense? So it was 180, 120, 120, 120. So I already told you. So this looks like this, 120. The bond angle is 120. So if there were 2 electrons up here, so that they would bend this down by pushing this down, and it would be like a pyramidal a little bit. Make sense? But since boron doesn't have a lone pair here, there is nothing to push this bond down. Everybody got that? So, like this. So ammonia, I just showed it. So this is the ammonia. So nitrogen here, hydrogen, hydrogen, hydrogen. So there is one lone pair. So you would expect, so there are 4 electron pair here. So you would expect 109.5, but there is the angle is not 109.5 because these 2 lone pair here push this guy more down, making the bond angle 107.5. Yeah, and it looks like a pyramid. Make sense? It's like a pyramid. So you put it here like that, and it's a pyramid. So if you look here, again, this one, see, there is no bond angle here. There is no lone pair here. So this is the linear. So look here, in the C, there is no lone pair here. So this is also linear. Look here, in the center C, there are also no lone pair, meaning there are no dots here. So this is also linear. Everybody got that? So I'm looking OCO bond angle here is linear. I'm looking FC C bond angle here, that's also linear, meaning 150. Good. So you need a model. So you need to buy if you are taking chemistry, maybe about $10, you can buy Amazon this model and display in home. Yeah, good. And in lab 13, we are just doing this thing. So we go there and we have a lot of models in the lab and we just play with it. So I already told this So this is the tetrahedral. Carbon is connected to 4. So 4 ways is 109.5. There are no lone pair in the center. And ammonia has 4 lone pair, 1 lone pair and 3 bond pair here. So they push this one, and down. So the bond angle is a little bit smaller than 109.5, which is 107.5. Since in water there are 2 lone pair, they push too much. to these bones, so the angle becomes even smaller down, so 104.5. Yeah, like that. Now let's go here. I already told you. So if there is a central atom and around that there are two, there are two something connected like this, right? So one pair here, one pair here. It's a linear 180 degrees. And if central atom is connected to 3, it is 120. If central atom is connected to 4, the ideal angle is 190.5. If central atom is connected to 5 like this, so these are in the equator, and this is going towards ceiling, this is going toward the ground. So this bonding angle is 90 degrees from top to equator. Bottom to equator is also 90, and the equator to equator is 120. Everybody got that? So if it is a central atom is connected to 6 ways, so this is electron pair, electron pair, electron pair, electron pair. So this is called, this is going up to the sky, this is going toward the down, and these 4 are in the equator. Yeah, so this is called tetrahedral, sorry, octahedral, and each bond angle is 90. Yeah, so I already showed this. Okay. Now let's talk about this one. So what happened here? So look here. So this one is this guy. So this guy, this one. So the first one is this guy. So 1, 2, 3 are there. One is going up, one is going down. So this guy is this one. So this is the trigonal bipyramid. So this is 1, 2, 3 trigonal, one pyramid under the pyramid. Trigonal bipyramid. So don't look this kind of picture. So basically they are showing the same thing here what I am showing. So let's go here. Now this is here. So they take this guy out from here. So there is nothing like this. So this position is only occupied by this position here is occupied by the electron. Yeah, there is no atom. So there is no atom here. There was an atom previously, but now there is only 2 electrons. So this guy looked like a seesaw. So when you were a kid, maybe you played the seesaw like this, right? So one friend sit this way, another friend sit this way, like this, right? So like that. So like this. So it looks like a seesaw. So one person sit this way, another person sit this way, and you play like this, right? So that's a seesaw structure. Make sense? So molecular geometry is seesaw, and there is a one pair of electron here, but no atom. Everybody got that? So seesaw. Good. And what is the bond angle you are expecting here? Again, so this is like this, right? So the bond angle you are expecting is this was 90, this was 90, this was 90, this was 120. But since this is there is no atom, so there is a one bond pair. So this bond pair is pushing all this bond a little bit down, a little bit down. So the angle becomes a little bit smaller than 20. Everybody got that? Good. So like that. Now, seesaw. Now let's look about the ClF3. So this guy is like that. So ClF3. So look here. So this looks like this one, right? So this there was a previously there was an atom. There was an atom here. Now there is no atom. There is only one pair of electron, one pair of electron. Now, although electrons are pointing 5 way, 1 way, 2 way, 3 way, 4 way, and 5 way. But look the molecule. How does the molecule look like? Like the T, right? The T. So they call it a T shape. Looks like T, right? The letter T. Everybody got that? T shape. So again, there are one pair electron here, another pair electron here. So they will push this all bond a little bit down and a little bit bent down. So it's a little bit smaller than predicted bond angle. All right, so how about this one? So xenon fluoride. So again, this one, look here. So now I'm going to take this out, and so there is one pair electron, there is one pair electron, there is one pair electron in the equator, and now although the electron pair looks like 1, 2, 3, 4, 5 trigonal bipyramid, the molecule looks like the linear, right? Like a straight line. Everybody got that? So the bond angle here looks like 180 degrees. Good. Now, how about the SF6? Let's look this one. So this is the SF6. So octahedral. So one is going towards sky down, and there are 4 here in the equator here. So 1, 2, 3, 4 equator. One is going toward the sky, and one is going down the ground. Now here, pull out this the atom going down. So just take this out like this. Yeah, makes sense. So there is only one pair of electrons hanging down here. So look here, how does the molecule look like? So there is a square. This is square, right? So it's square. This is square and it's going up here. So this is square and it is pyramid, square pyramid. Everybody got that? So 1, 2, 3, 4 are in the plane here. So this is a square and this is going up is a square pyramid. Good. So now again, a bone angle will be little bit smaller than predicted by that 6-way figure. So because there are the lone pair here, so those lone pair will be pushing this guy a little bit down, a little bit down, a little bit down. So it's distorted a little bit from 90 degrees, maybe 9.5 degrees, something like that. Everybody got that? So let's look the square planar. Now take out another one from here. Just take out it and throw it like this. Now it becomes like this one, right? Look here, this one. So there is one pair of electrons, there is another pair of electrons. Now these 4 are in the one plane. So this is a square. So this is square planar. They call the plane. All are in the one plane. So this is square planar. Make sense? So again, now is the bone angle is 90 degrees. So you would predict by the this structure if bone angle should be 90 degrees. But since you have a one pair, lone pair here, so they might be distorted a little bit or not, probably not, because whatever the lone pair from down pushing this way up, with the same force, there are other lone pair, they are pushing this bone pair down, so maybe push up and push down is same, and so this molecule all is 90. Bone angle is 90. Everybody got that? So like that, yeah. So this is a PCl5 molecule. So what is the PCl5 molecule? So I already showed you. So this guy. So this is a 5 atoms are connected with this guy, and the center one, and looks like this. So when you look the book, they write like this way, but in reality, the molecule looks like this way. Make sense? So this is the central atom of phosphorus here. This is of chlorine. This is chlorine. This is chlorine. This is chlorine. Chlorine here, and this is the PCl5 looks like it. So this is a trigonal. So look here at the equator, trigonal pyramid. Down is the pyramid, trigonal bipyramid. So book may write like this, but structure is reality. Anybody got that? So sisa, I already showed you the sisa. So you take out this one and you have just like this, and it behaves as a sisa. Have you got that? Just like that. Now, what I here? So I think we already talked about this one. So square parameter. So this is SF6. I already talked about the bone angle. You can say square bipyramid, or they call the octahedra. Octahedron and square bipyramid is same. Yeah. Good. So you need to have a model. Without a model, it's impossible to learn this chapter. Yeah. So now, how does the SCl2 looks like? So SCl2. So here is a S sulfur and group. This is the group 6 element. So here is chlorine. Here is chlorine. So you might write something like this. But so this one electron coming from sulfur here, one is coming from here. So sulfur has 6 electrons outside. So 2 are the lone pair here. So they are just pushing them down, and this is a bench structure. Bench structure, right? But you would predict at the beginning. So this is 1, this is another domain, this is third domain, this is the fourth domain. So you may say, oh, there are 1, 2, 3, 4. So this is the tetrahedral. You might predict this is the tetrahedral, and you say, oh, bone angle should be 109.5. But that's not true. So this position is occupied by the lone pair. This position is occupied by bone pair. So it's not 109.5. It's smaller than 109.5. Smaller than maybe it's about 105 degrees, something like this. This bone angle, yeah. Because then this bone pair are just pushing this bone pair down. Great. Everybody got that? Right. So this is bench. Alrighty, so we are done with the molecular structure. Now let's go to the electronegativity. So what is the electronegativity? So you will repeat this in the lab 13. We have too many molecules to work with this model in lab 13. So you will be repeating all what I just told you. So first of all, we need to know how many pair of electrons around the central atom, and then you need to start to distort the shape by taking each atom, right? Now, electronegativity. So what is electronegativity? So electronegativity is something like this. Let's say hydrogen and chlorine are making a bond. So chlorine is giving one electron to hydrogen. This electron to this. This is the electron of chlorine. So this chlorine is giving this electron to hydrogen, and hydrogen have one electron, and this hydrogen is giving this electron to chlorine. So they are exchanging. So this is going this way, this is going this way, this is going this way, this is going this way. So they are giving one bond like this. Make sense? That's how they share the electron. Now, where are these two electrons? So most of the time, where are these two electrons? One is sitting here, or one is sitting here, or is it sitting like this, or it is these two electrons are sitting like this? So how do they sit in real life? So they don't sit like this. The electron is not here. The electron is not here. The electron is not here. The electron is not here, so electron don't sit like that way. So what people found is that those electrons are so most of the time, if the element are same, so this is hydrogen, this is hydrogen, so both are same element. If both elements are same, both the electron from here and here, they exactly sit at the middle like this, at the midpoint. Make sense? But if they are not same, so what happens is this electron don't try to sit exactly in the middle, so it's drifted slightly toward the chlorine like this. So this is called the electronegativity. So who has more electronegativity here? So the chlorine pull this shared pair of electrons more toward itself than hydrogen. So this capacity of pulling of shared pair of electrons by one atom is called the electronegativity. Everybody got that? So if you have a sister and you are playing something and somebody pull the more toys toward her, so that she has the more electronegativity. Yeah. So look here. So they give some scale here. So lithium has 1 electronegativity, beryllium has 1.6, boron has 2, carbon has 2.5, nitrogen has 3, oxygen has 3.5, fluorine has 4. So who can pull those shared pair of electrons with great force? Fluorine. Yeah. So if you make a bond between fluorine and oxygen, so the fluorine and oxygen. Let's look here, fluorine and oxygen. Look here, who has the more force to pull the electron? Fluorine has 4, oxygen only 3.5. So oxygen is weak, fluorine is strong. So those electrons try to sit near fluorine like this. Make sense? So whoever is the stronger to pull the electron, those shared pair of electrons sit more toward that guy. So this guy will be a tiny plus, and this guy will be a tiny minus. So probably you already studied the water. When you are writing the water, HOS, so you are writing like this, tiny plus here, and tiny minus here, right? So why that happens is because this shared pair of electrons here don't sit exactly at the middle, don't sit toward hydrogen, they sit close toward oxygen. Same here. So this electron, those negative charge, sit close toward oxygen. So this has a tiny minus, this has tiny plus. Everybody got that? So it the polarity of we call a polarity, right? The one is a plus here, another is a minus here, meaning we have a polarity. So the polarity coming from the capacity of the elements to attract the shared pair of electrons toward themselves. Good. So whoever cannot has a less capacity to attract electron has tiny plus charge. We even have bigger capacity to pull the electron to them that have a tiny negative charge. Easy. Now just look here. So all the things, all these are the electronegativity scale is given here, and we will just use this. So what happens to electronegativity? Electronegativity increases as you go from left to right, and electronegativity decreases from we go from top to bottom. 1, 0.9, 0.8, 0.8. Here, if you see here, 0.9, 1.3, 1.6, 1.9, 3.2. So this group has very high electronegativity, right? The electronegativity decreases from top to bottom and increases from left to right in the group. Everybody got that? Easy, right? Now let's go here. So you can just read yourself here. So if the electronegativity between two is 0, so let's say hydrogen is electronegativity, how much in hydrogen? So we go back and so here let's write the I have hydrogen. Hydrogen is 2.2. The electronegativity of hydrogen is 2.2. So I am making the bond between two hydrogens. So here is one hydrogen, here is another hydrogen. So 2.2, this guy has electronegativity 2.2, this guy has 2.2. Now subtract from this to this, 2.2 minus 2.2, that's 0. So if the electronegativity between these two bonding atoms is 0, those electrons exactly sitting at middle position of this element, and this is a pure covalent bond. So it's not ionic. So if you put in water, it doesn't conduct electricity. That means that. Yeah, covalent means when you just dissolve in water, they don't conduct electricity. Good. Now let's go and look another one. So purely covalent. A difference of 0.1 to 0.3 indicates the non-polar covalent. So let's go here. Do I have something? Let's look here. So non-polar covalent. So anyway, so they take two elements and subtract from one to another, and if you get the electronegativity difference, still that's a non-polar. This is a very, very purely covalent, and still this is non-polar covalent. Still it doesn't conduct electricity in water. Yeah, non-polar covalent. Now let's go here. A difference of electronegativity between 0.4 to 1.7 indicates that the bond is a polar covalent. Now it is a polar covalent. So this is important here. 0.4 to 1.7. Let's look at S and F. So S and F. So S and I have F. So look the what is the electronegativity of F? That is 4. And what is the electronegativity of hydrogen? That is 2.2. So the electrons are shared in between here. So who will pull this electron? So 4 minus 2.2 would be 1.2.8. No, 1.8, right? 1.8. So the difference between this is 1.8. So this guy has more electronegativity. So these are pulled more toward this guy. So if you draw the picture, so this looks like this. So this is basically saying the electrons are more pulled toward fluorine than hydrogen. So you see that the balloon, so the balloon looks like bigger in this side, right? So those electron density, so maybe they are jumping around here, here, more time than this way. Everybody got that? So this is polar covalent. Now, if you put HF in water, they immediately break and start to conduct electricity. Polar covalent. Yeah. So if you do the lab number 4 with HF, you will see the large conductivity conductivity data. Yeah, like 2,000, maybe 4,000, 8,000, right? So we'll work that way. Now, this I told you, if you put the hydrogen in water, and put the probe and measure the conductivity, how you measure in lab 4, 0. You'll get like water, even smaller than water, 0, right? Now let's go here, Li and F. So this is polar covalent. Now this is pure ionic. So electron is completely drift from lithium to fluorine. Look here, a difference of electronegativity greater than 1.8 is a pure ionic bond, very ionic bond. So look here, Li is how much Li? So let's go here. Li is 1, F is 4. LiF. So Li is 1. Sorry, Li is 1, F is 4. So 4 minus 1 is 3. So the lithium electron is completely transferred from lithium to fluorine here. So this is separate, this is separate. Now this guy has plus charge, this guy has negative charge, plus and minus. Now attract each other. So it's a purely ionic compound. Electron is completely transferred from lithium to fluorine. Good? Everybody got that? So this one electron is not completely transferred. The electron is just moving like this. Sometimes they go HF like they are moving and moving, but most of the time they spend their time around F than around X. Yeah? Good? like this. So I will put in exam. So okay, this is the element. Do you expect that the compound between SA and Cl is covalent, purely covalent, or ionic, or what type of bond you would expect? Yeah. So you just put the number there and get the difference, and maybe you want to take this note here. So if you get the zero difference, that's a purely covalent. If you get the difference 0.1, 0.2, or 0.3, you will say, oh, non-polar covalent, meaning that they don't conduct electricity. If you get this one, polar covalent, and this is a very ionic, so decompose in water and conduct electricity. Yeah, good. So I write this one the same thing here, so you can just do the difference. So what is the greater the difference of electronegativity, the more polarity of covalent compound. So the difference of electronegativity H and F is 4, H is 2.2, this is 1.2. So if you do the same calculation for C and F, C is here, F is here, H is here, so the difference will be 1.5. If you do the O and F, so O is 3.5, F is 4, so the difference will be 0.5. So which is the more covalent, more polar? So this is a very polar compound, right? 1.5. So they conduct electricity very good in water. So this a little bit, they conduct electricity, but a little bit OF probably doesn't take. It's a really small, right? 0.5. Everybody got that? So it's just like the tug of war. Yeah? So like the pulling the rope by two. So HF is highly covalent. CF is a little less covalent, OF is really less polar, not covalent. So this is a more polar, less polar, least polar. Polar means in this one, there is a lot of positive charge in hydrogen, a lot of negative charge in hydrogen. But here, if you look O and F, O has a small amount of positive charge, F has a small amount of negative charge. Charge is not separated here. Everybody got that? So polar means one guy has a more plus charge, another guy has more minus charge. Like this. So polar means, so it is very important concept, and we will be doing again and again. So if you write this one, so if you say HCl is a polar compound, so we write slightly positive, small plus charge here, slightly minus charge here. So this is the polar compound. That means the electron between hydrogen and fluorine are not exactly between, they are spending more time around fluorine. Yeah. Good. So lab 13, in the lab 13, we will be doing all this kind of calculation there. So look here, HF. So you can easily do this kind of thing. So look at HLF electronegativity, and if look the rule here, and if you get 0.4 to 1.7, they are polar. Yeah. So HF, this is 0. Polar. Let's go here. So 0.4 to 1.7. 0.4 to 1.7. Look here, 1.7 polar, 1.07 polar. So HBr 0.4 to 1.7. This is polar. This is 0.4 to almost polar. HI is almost polar, right? It's HI 0.38. What is 0.38? 0.3. So it's 0.38 close to 0.4. So that's polar covalent. Yeah, 0.38 is close to 0.4, right? So this is 3.38 is 0.38 is 0.4. Yeah. Now let's go here. Hydrogen. Hydrogen is one hydrogen is 2.2. Another hydrogen is 2.2. 2.2 minus 2.2 is 0. So this is 0. This is purely non-polar. It's covalent. Pure covalent. So look that rule, and so like that. Now we will talk about the molecule there, whether NH3 is a polar or not, NF3 is polar or not, BF3 is polar or not. So we need to treat this molecule a little bit different way. I just talk about the bone polarity, right? I have just two things here. So X is here, Y is here. The electron is sitting maybe near this one or near this one, and I just did one bond, right? I have not talked about them as a whole, whether the molecule is a polar or not polar. So let's go there and talk polarity in molecules. So let's go down here. So let's look here. So bone and molecular polarity. First of all, you need to calculate the bone polarity, whether the bone is polar or not polar, right? So let's talk about the BF3. So we are really moving fast, and maybe next class we will finish chapter 8 and start chapter 9. So let's talk about the BF3. B, F, F, and 3. So this is like this one. So BF3. So I told you. So this is a B. So we need a model. We need a model for this one. Yeah. So BF3. So do you think now let's calculate the whether BF bond is polar or not. So let's go to B and look BF. So B is 2, F is 4. 4 minus 2 is 2. So anything that falls between 0.7 to 1.8 is a polar, right? So according to the rule. So this bond is polar. This bond is polar, this bond is polar, this bond is polar. So meaning that this electron here are sitting, this is a BF3 molecule. So this electron here are sitting not like this. So these are sitting more toward this side, more toward this side, because F has more pulling capacity, and F has more like this one. Now imagine that. So this is like this one. So one person is pulling this way, another person is pulling this way, another person is pulling this way with equal force. Would this molecule move? It will not move anyway, right? So they call the vector sum of in this. So if you have taken already the math course in vectors, they call okay. If I add this pulling force this way, this pulling force this way, this pulling force this way in this one, and I add this 3 force, that is 0. So they call vector addition of. So this is one vector, another vector, another vector. But you don't really have to understand that one. Imagine that there are 3 things, and it's kind of the balance. So however, so maybe if this electron are pulling this way by 1 Newton force, this electron are pulling this way by 1 Newton force, and this electron are pulled this way by 1 Newton force. If 3 way are pulled with equal amount of force, so the net pull is 0 according to the vector addition. So it will not move anyway. Make sense? So this the molecule, since this is a planar molecule, and they have all pulling with the equal force this way, equal force this way, equal force this way, and if it is pulled 3 way with equal force, the polarity is cancelled. So it's a 0. Make sense? So like that. So how about, so rather than that one, so we could just do something like this. So let's say this one. So I have like this. So let's say I have Cl here, and I have H here, and I have H here like this, and no, I want to put something different here. So S, and this is let's say F, and this is F. So let's say they are pointing like this way. So center atom is S, and this is F. So the electron is more pulled toward this. So maybe electron are here. So maybe electron are here. So this is pulling this way, and this is pulling this way. So one person is pulling this way, and another person is pulling this way with equal force. Does it move? It doesn't move, right? The tug of war is just they are pulling opposite side with equal force. So this guy doesn't experience any pull. Make sense? So doesn't experience any pull in either side means it's a non-polar. Make sense? So molecule as a whole, this is non-polar. Although this bond is polar, this bond is polar, this bond is polar, but this is being pulled this way, maybe by 10 Newton force. This is being pulled by 10 Newton force. So this is pulling to each side 10. So you get plus 10. If this is going to this way by minus 10, so minus 10 and plus 10 is 0, right? So that's a non-polar. Everybody got that? We are being pulled both ways. Yeah. So how about this one? If I hold like this one, what happens? This is pulling down. This is also pulling down, right? Now this is pulling as a whole toward the ground. So this is the polar. Everybody got that? Just like that. Yeah. So imagine that a tree. You have a tree, something like this, a small chicle, which is a weak tree, and it has some branches. So in this way, the fruit is, let's say, 5 kg mango is here, and this way there is only 1 kg mango is here. Is it a polar or non-polar tree? is a polar because this tree will bend this way, right? Everybody got that? So it's a polar now. But if you see a tree like this, let's say you have a branch here, another branch here, and then this way, 5 gram, this is also 5 gram. So this tree is not neither bent this way nor bent this way. So this is non-polar tree. Everybody got that? Good. So we will talk a little bit in the next class about this polarity, and maybe we. All right. So 46, I think we can stop now. Yeah. So try this one, and we'll talk more there about this polarity. And in next class, I think I will finish the chapter 8. And then chapter 9 is not that understandable, so we'll